So organic chemistry. If that word makes your brain freeze up thinking you have to memorize millions of complex molecules, I want you to just stop. Think of it less like a boring textbook and more like a massive box of Legos. It's a logical system with some really simple rules that lets you build an almost infinite universe of structures. And when I say a universe of structures, I am not kidding. The scale we're talking about is just massive. To give you an idea, get this, a whopping 90%
of all known chemical compounds on Earth are organic. Now, how is that even possible? It's all thanks to one special element, carbon. It's a master builder that can form 4 super strong, stable bonds, creating these long chains and complex rings. We're talking about pretty much everything, from the plastics in your pocket to the medicines that keep us healthy, to the very DNA that makes you, well, you. It's the chemistry of carbon, and it's literally the chemistry of life.
Okay, so having millions of different compounds is incredible, right? But for a chemist, that's a huge headache. Imagine trying to find a specific book in a library with millions of volumes, but with no card catalog, no system whatsoever. It would be total chaos.
So, that's the big question, isn't it? How on earth do chemists make sense of all this variety? Do they really have to memorize every single one? No way. The answer is so much smarter and more elegant than that.
They've found a way to tame the chaos. They classify everything into families based on how they're built and how they act. So instead of memorizing millions of individuals, you just learn the family rules. It's a brilliant system, and it all boils down to 2 really simple but super powerful ideas.
The first idea is something called a homologous series. And really, you can just think of this as a family of molecules. You know how people in a family kind of look alike and share certain traits? It's the exact same idea here. All the members have the same basic formula, a similar structure. And because of that, they all behave in really predictable, similar ways.
So let's meet the most basic, fundamental family in the entire world of organic chemistry, the alkanes. These guys are the simplest of the simple. They're just made of carbon and hydrogen atoms, all linked up. Think of them as the foundational 2x4 Lego brick that you can build almost anything else on top of.
Okay, let's take a look at this. Up top, we've got methane, 1 little carbon atom. Then you have ethane with 2, propane with 3. You can see the pattern, but look closer at the actual structure. To get from methane to ethane, you basically just stick a CH2 group in there. To get from ethane to propane, you do it again. It's this super simple, totally predictable pattern of growth.
And like any family, the alkanes have their own set of rules. First, they're saturated. That's just a fancy chemistry term that means they're holding on to as many hydrogen atoms as they possibly can, connected only by single bonds. They all follow one simple formula, CnH2n+2, and they all share the same last name, the suffix, ane. Their first name, the prefix like math or eth, just tells you how many carbons are in the chain. Simple, right?
Okay, but here's where it gets really, really interesting. What happens if we make just one tiny little tweak to that basic structure? What if, instead of only single bonds, we introduce just one double bond between 2 of those carbon atoms?
Well, that one little change creates a whole new family, the alkenes. Now, they're called unsaturated because that double bond means they aren't holding the maximum number of hydrogens anymore. Their general formula changes to CnH2n, and their family name, that suffix, becomes ene. One little change, a whole new family.
And this side-by-side shows it perfectly. On the left, you've got ethane. See that single line between the carbons? That's the single bond. Now look to the right. That's ethene. Those 2 lines, that's our new double bond. And that one little difference makes ethene way more reactive and creates a completely new homologous series with its own unique personality.
So if homologous series are the basic families, how do we create even more variety and cool new properties? Well, this brings us to our second huge idea. We add accessories. In chemistry, we call them functional groups. And trust me, these things are absolute game changers. So what is a functional group? It's just a specific little cluster of atoms that you can snap onto a carbon chain. And here's the magic. That little group is the part that does all the work. It's the active, reactive part of the molecule. It basically decides the molecule's personality, how it's going to behave, and what kinds of chemical reactions it's going to get into.
And this quote right here ties our 2 big ideas together perfectly. A homologous series isn't just a bunch of molecules with the same carbon backbone. It's a bunch of molecules that all have the exact same functional group. That's why they act like a family.
They all have that same active ingredient that defines who they are.
Let's actually see this happen. Here's our old friend ethane again, from the alkane family. Remember, it's a pretty boring gas at room temperature, not very reactive, just a simple 2-carbon chain. This is our before picture.
And now, let's play with our Legos. We're going to pop off one of those hydrogens and snap on an OH group instead. This little guy is called a hydroxyl functional group. And boom, just like that, ethane is gone. We've made a totally new molecule, ethanol. And you have to appreciate just how big of a deal this tiny change is. Our boring gas, ethane, has now become ethanol, a liquid at room temperature. It's not an alkane anymore. Its new family is alcohol. The name even changes from ane to anal. And because that OH group has a slight electrical charge, it's attracted to water. This means ethanol can dissolve in water, something ethane could never ever do. This is where the real power and creativity of chemistry comes into play. You see, the OH group is just one tool in a massive toolkit. Chemists have a whole collection of these functional groups they can use to design and build molecules with whatever specific properties they need.
I mean, just look at this. Every single one of these functional groups creates a brand new homologous series. Slap on a COOH group and you've got a carboxylic acid, think vinegar. Add an NH2 group, you get something called an amine. Each one is a different Lego piece that gives the final molecule a totally new job, turning this simple carbon chain into everything from acids to flavorings. So, what's the big takeaway here? The main thing to remember is that organic chemistry is not about memorizing millions of molecules. It's about learning a system, a language. If you can really get your head around these two core concepts, homologous series as the families and functional groups as what gives them their character, you've basically learned the grammar. You can start to predict properties, understand names, and see the beautiful, simple logic behind the whole thing.
So in the end, it's not about memorization at all. It's a logical system of building blocks, a kind of chemical Lego, right? And that leaves us with a really fun question to think about. Now that you know the rules, what could you build?